Okay, friends, we are going to look at the next section in graphing, and this is concavity and points of inflection. So both of those terms may be new to you, and so we're going to dive right in. So some of the new terminology you're going to want to be paying attention to today is the term point of inflection, concavity, concave up, concave down. And also, we're going to do a review of increase and decrease. And we're also going to try to see if we can find whether something's relative min or max without actually graphing. See if you can do that. Okay. So first things first, let's make sure we define concave up and concave down. And you can see here that this blue area is concave down, which we can see that it's pointing down. This curve points down and this curve points up. So that's what concave up and concave down mean. In terms of a graph, this blue area here would be concave down and this would be concave up. And this point right in the middle, we would call a point of inflection. Okay, so right in between the concave down and the concave up, we would call a point of inflection. So in previous chapters, we were looking at particles moving and we talked about acceleration and velocity. So if we were to say, hey, where's the acceleration negative here? We'd say it's negative right here. Okay, so it's kind of, the slope is slowing down and the slope is speeding up. So we'd say that it was accelerating when x is larger than -2, and it's decelerating when x is less than 2, -2. Okay, and so intervals of concave up, concave down are the same. So right here we'd have the interval is, it's pointing down here, so it's concave down to the left of -2. Okay, so these are sort of warm-ups, and remember that coordinate -216 is the point of inflection. As you go through this video, please pause at the start of each challenge to sort of give it a go on your own first and then compare with what I'm thinking. Okay, second derivative test. The second derivative test allows us to determine whether a critical number is a relative min or max without actually graphing. Let me show you how that works. The explanation in the slide deck is maybe a little longer than I was hoping, so I'm just going to do it here. So pay attention to this red curve, and this is the second derivative. Notice that when x equals -1 here, we're at a relative maximum. You can see that with your eyes. Look at the second derivative. The second derivative is negative. So what that tells us is if the second derivative is negative, then it's going to be a relative maximum. If the second derivative is positive, then the critical number that we'd put into the second derivative would create a minimum. I'm going to say that one more time. We can see that this has a critical number of -1, and let's pretend we don't know what the graph is. So we're wondering, is -1 a relative min or relative max? Notice that when we put -1 into the green line, the second derivative, that we get a negative value. Okay, so a negative second derivative means that it's concave down and there's going to be a local maximum at that critical number. On the other side, let's hide the graph for a second. We know that it has a critical number at, say, 0.75. So at 0.75, we have a positive second derivative, which means it's concave up, which means that's a relative minimum. So I hope that helps you in your understanding. If you'd like a little bit more practice, you could look at the slide deck through here, but I think for the sake of our time, looking at Desmos is just great. So take a pause the video, and then let's walk through these questions together. All right, here we go. So approximate the intervals. Approximate the intervals where the graph is concave up. I need to change that. So where is it concave up? It's concave up in 2 spots, here and here. So approximately, it's going to be concave up from this region here, and concave down in the middle with 2 points of inflections right there. Okay. Pause the video pause the video again. Okay, on what intervals is it concave up? Well, we have multiple concaves up, one there, and I think this graph shows it nicely. Concave up in blue, concave down in red. Alrighty, now what we're going to do is we're going to use algebra to determine the intervals of concave up and concave down and points of inflection. So pause the video, and I want you to do a sketch of this, and then we'll connect in just a moment. Okay, welcome back. So what we're going to do to start off with, is look at the algebra. Do I do the, oh, I did not do the algebra here. Okay, so I'll do it over here for us. So if we're trying to find the intervals of concave up, concave down, the very first thing I would do is do a quick sketch of it. It has a y-intercept at -12. It's degree 4. It's positive. So it probably looks something like that. It could look like that. It could look like this maybe. Maybe it looks like that, you know, and it could be shifted over to the left more. So that's the general shape. So that's what I'm expecting to find. So I'm expecting one concave down and 2 concave up. That's what I'm expecting. And I'm also expecting 2 points of inflection. So I'm going to take the first derivative using my trusty mouse here. And I hope you've paused this video so that you're doing this on your own first. If you're looking to develop your brain and make connections between ideas, you have to figure out what you don't know first before just listening to what someone else thinks. So come to your own conclusion first. So that's the first derivative, which tells us about intervals of increase and decrease. That does not tell us. So now I'm going to take the second derivative, which I should have gone prime, but I used 2, which could also work. So now I'm going to take the second derivative, 12x squared minus 6x minus 3. Okay, now what I'm going to do is I'm going to factor this. I'm going to take out a 3. Oh, I do not like this. This is going to be 4x squared minus 6x minus 3. Okay, no, minus 1. And I don't like that. Did I make a mistake? Oh, that's supposed to be a 2. Okay. And that's looking better. Okay, so now I need to factor that. I need 2 numbers that multiply to 4 and add to negative whatever. Okay, friends, I'm just looking at my work and I realize I made a mistake. So I'm just going to start this over. You probably caught it. So let me do that again. So this is going to be 4x cubed minus 3x squared minus 6x plus 1. That's the first derivative, f prime. Now we're going to look at the second derivative, double prime. So that's going to be 12x squared minus 6x minus 6. That looks better to me. So thanks for staying with us and not giving up on me when I made the error there. We're going to take out a 6 now, okay, to factor, because remember what we're doing. We want to figure out where the second derivative equals 0, because this is going to help us find our numbers where which basically the spot where the points of inflection are. So it's going to be 2x squared minus 1x minus 1. So I need to factor that. Okay. Okay, so we're going to have 2x. Doesn't look like I have a lot of options here. I need 2 numbers that multiply to -2 and add to -1. So I am going to factor this, and I'm trying to do it in my head. Let's see how it goes. So I guess I need I think I'm going to make this a negative and this a positive. Let's see if that works. So that gives me -2 squared, that gives me -1, that gives me -2, perfect. So that tells me that the points of inflection are going to happen when x equals -1/2. And remember, a point of inflection is in between concave up and concave down. It's kind of like the critical number for intervals of increase and decrease. So here are those values, okay? So now you can see here what I'm going to do is I'm going to make my little guy here with my intervals. Oh, and remember, friends, I knew that this graph sort of looked like this, didn't I? I knew that. That's how I'm making this decision. Okay, so when when I have my -1/2 and my 1, I'm going to put these values back into the second derivative to sort of make sense of and guess, right? Basically, when I put this value in the second derivative, if I put values to the left of here in the second derivative, if it's positive, it's concave up. If it's negative, it's concave down. Since I know what this graph looks like, I know that it's going to be concave up when x is less than -1/2, and it's going to be concave up when x is larger than 1. Okay, so that would be an important observation. So if we went back here, we're going to leave it at that. Okay, so let's continue. Let's look at a more challenging example. So once again, we know that our this is our region where it's concave up, concave down in the middle, and concave up. And if the second derivative is negative, then the interval is concave down. Conversely, if the second derivative is positive, then the interval is concave up. Okay, this is going to be a tricky one, no doubt about it. So determine the points of inflection here. Determine the points of inflection. So what's tricky here is we don't know what the graph looks like. So feel free to graph that on Desmos, but you should be able to find this to be able to visualize what a point of inflection is, even though we don't know what this graph is, and neither do I. Okay, so what I'm going to do is I'm not going to do it here. I'm going to just talk you through the PowerPoint. You don't need to know what this looks like, but even here, I hope you can tell how tricky this is to figure out where it's concave up and concave down. It's clearly concave up there. It's concave down there. But do you notice here that at a certain point, it's going to go back to concave up over here and concave down over there. So I'm expecting basically 3 points of inflection. Okay, so here we go. So first things first, we need to take the first derivative here. So the quotient rule needs to happen. So we're going to do that. We're going to simplify it. It looks like this. Then that's the first derivative. The second derivative, we need to repeat the process, and it's going to get bigger. It's going to get, it is. We're going to clean this all up. So let's just be clear here. Actually, I'm assuming that you remember okay. So this is F, and this is G. So this is F prime times G minus F G prime over G squared. That's the quotient rule. And then what we're going to do is we're going to expand these terms out, collect like terms. And so that's what we've done. Okay, that's simplified. There's no need to expand the bottom. Now this is the new F, and this is the new G. So now we're going to take the derivative of that. So this is going to be F prime G minus F G prime. And don't forget the chain rule right there. And we're going to expand that all out and clean that up. So at this level here, remember, we're going to set this equal to 0. When we cross multiply, this times 0 is 0. So now we just have this thing right here. We're going to collect like terms. So we get this. Then what we're going to do is we're going to factor out a 2x. So we're going to have one of the critical numbers is going to happen at 0. Not critical numbers, points of inflection. It's going to happen at 0. Then we're going to take this guy. The other one is going to be, if we factor that, it's going to be you're going to have x squared minus 3 equals 0. So we're going to have x squared equals 3, and we're going to square root that. Okay, so let's go into Desmos just to check the solution. I want you to put your solutions in so that you can get those coordinates, okay? I have included the answer there for your reference, but there they are, okay? And so I'm assuming that you know how to put, if we put 0 in here, that's one of the coordinates. Oops, why isn't that working? That's a 0, 0. And then it's the square root of negative square root of 3, and this is the positive square root of 3, and there are those values. So the answer, the coordinates would have been negative square root 3 and negative 0.433, blah, 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 0, 0, and this value here. So concave up, concave down is algebraic, it's tricky, and requires you to do many competencies. You need to be able to take an equation, turn it into a graph, and visualize all these difficult pieces. Plus, we added a bunch of new terminology today. So all in all, it's a pretty tricky lesson. Good luck, and we'll see.